Hello there, this is Tyler Jones from the University of Illinois Springfield. Today we're going to be working with a molecule and determining mass spec, IR, proton NMR, as well as carbon NMR. That way we can find a proper structure for this molecule. So without further ado, let's get started. Alright, so today we're first going to start with looking at mass spec. And first I'm going to label our structure. The structure today is going to be C6H12O2. So with mass spec, we're going to work right to left. The first thing that pops out here on the right is this final peak right here that says 116. This is actually going to be our M plus peak, which labels our molar mass. And if we do the math, we'll see that C6H12O2 does equal 116 for its molar mass, so that's perfect. Secondly, we want to label the base peak. Our base peak is always the highest peak in mass spec, so that's going to be right here with this number 70. Label that as the base peak. And we'll draw a little connecting line to our M+, just to know that that's there. The difference in the math there is 46, which, referencing Compound Chem and their mass spec worksheet, 46 does not represent any particular structure. So I'm just going to write nothing there as a little side note as to that will not be important to me. And then also we have some pretty good size peaks in between our base peak and M plus peak of 98 and 83. So we're going to label from our base peak to those as well to see if those differences represent anything. After doing the math, we'll see that this difference is 28, which also Compound Chem says that that represents no structure. So I'll label it quickly as nothing, just so I don't get it mistaken with anything. Same thing here, the difference here between 70 and 83, 13. Again, this represents nothing as well. Also, what we'll take a look at here is the degrees of unsaturation, because that is arguably the most important part of mass spec. Degrees of unsaturation typically tells you how many pi bonds and or ring structures you have. So the formula for that is 2 times the carbons plus 2 plus your number of nitrogens minus your number of hydrogens minus your number of halogens, and that is all divided by 2. So if we plug in here, we're going to have 2 times 6 carbons plus 2 plus 0 nitrogens minus 12 hydrogens and minus 0 halogens, all divided by 2. This gives us a degrees of unsaturation of 1. So this can mean one of two things, having only a 1 degree of unsaturation. This means that we are either going to have 1 pi bond or 1 ringed structure. So that's good to keep in mind. Okay, so now we're going to move on to IR. Label that for us. So in the meantime, I went ahead and labeled all of our zones at their respective markers, and I labeled those numbers. This, what I followed was found from Compound Chem as well, their IR worksheet, so that can be referenced as an outside source for this as well. So we're going to dive on in here, working from left to right. We're going to label the zones, and then we're going to take a look at what our peaks tell us and what we could possibly have in our structure. So right here for zone 1, we have a nice large peak which has two forks coming down. Those two forks are very important as they directly represent the possibility of two alcohol groups. And considering this is such a large peak, we can think of that as a very high possibility. So I'm going to write that here. In zone 2, we also have nice peaks to show. There's a couple more possibilities here, such as an alkane, an aldehyde, and even a carboxylic acid. Zone 3, we have near no peak or peaks here. This is a very high signal, so we're just going to label this as no signal. Zone 4, right here between 1650 and 1850, we also really do not see anything. That's going to be no signal as well. And in zone 5, right here, 1450 to 1650, we do see some peaks here, right here at 1453 exactly, and that gives us the potential for an alkane as well. Or potentially even an aromatic, because our 1 degree of unsaturation that we saw in mass spec does leave that possibility. Finally, over here to the right, outside of the 1450 and down through the rest of the graph, this is labeled as the fingerprint region. Typically, the fingerprint region is ignored. Sometimes there is a possibility of being able to read some sort of structure that could come out of it, but as we reference compound chem again, there's nothing here, so we will not worry about the fingerprint region. So now that we have completed mass spec as well as IR, we are going to move on to proton NMR. Okay, now that we have taken a look at mass spec as well as IR, we're going to move on to proton NMR. This is arguably the most important step of this entire process in determining the structure of C6H12O2 because it really gives us the most information on things such as de-shielding, proton integration, symmetry, etc. So let's just dive on in here. First I'm going to label to make sure this is labeled as proton NMR and that we are working with C6H12O2. Also, an additional note is on proton NMR, we are going to be working from right to left. So first, what I want to do, just to get a couple of housekeeping things out of the way, is I want to label the number of peaks here. As we can see, these peaks appear to all have a singular, very portrayed peak, so we're going to label all 5 of these as singlets. And an important note to make is we are going to ignore this outlier peak as it's not labeled with an integration and doesn't apply to this structure. So I will quickly label these all as singlets. Okay, now that we have that out of the way, now it's time to try and determine the structure. So, for my guess, we need to remember back to mass spec as well as IR. In mass spec, we found our degrees of unsaturation be 1, which means we have 1 pi bond or 1 cyclic structure. Considering we did have in our IR a peak in the aromatic region, I think it is probable that it could be the aromatic ring. As well as in IR, we had a very prominent peak or tongue of peaks in the alcohol group. So this tells me two things: that we most likely have a ring, and there's a very high chance for two alcohol groups considering we have two oxygens. If this is the case, we're going to have three different types of structures: meta, para, and ortho. So I'm going to go ahead and draw those now. So first, for meta, or with a space in between, go ahead and draw that. We're going to have one alcohol group here, as well as one alcohol group here. For para, they are going to be on opposite sides. And finally, for ortho, they're going to be on the same side. Now, when we look at these, and then reference our actual proton NMR graph here, it really doesn't help us too much in trying to determine as to how the protons in these structures are deshielded. So, what must be done is the drawing of a chair structure. So I'm going to go ahead and do that. And if we remember, in the rules of a chair structure, adding in the alcohol groups, one must be axial and one must be equatorial. Now this is much more helpful when it comes to determining deshielding, because if we remember, an axial group is closer to other groups, such as the other carbon groups with protons, than is the likes of this equatorial alcohol group. So now that we have that drawn, we are going to go ahead and do the N+1 rule. But first, I just want to do a couple more housekeeping things. I want to make sure to label the integration here to make sure we do have the right number of hydrogens: 2, 4, 6, 8, 12. Perfect. 12 hydrogens or protons. As well as I want to label in the hydrogens on the chair structure to make sure those are correct as well. Filling the octets. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. That structure lines out well. So now that we have this, we're going to move on to the N+1 rule like I mentioned, in the hopes that it will help us line up with these integrations. It may not, but we will see. And to do that, referencing a proton, one looks at the adjacent carbons and its protons and takes that number +1. So for these two, they are both going to have an N+1 rule of 3 + 1, it's 4. Again here, 3 + 1 = 4. These two groups are going to be the same as well. And these two groups are actually going to be 4 + 1, which = 5, of course. Okay. Now that we have that, it's actually time to start trying to figure out what protons go where. So again, working from right to left, all the way to the right is going to be the least deshielded groups, which of course makes sense to be these two groups, as these 4 hydrogens match up with the 4 hydrogens on this integration, and they are the farthest groups away from these alcohol groups with the very electronegative oxygen atom. So we're going to label in green these two proton groups to go all the way to the right in the least deshielded position. Just switching colors here. Now, moving to this left group here from the most right, this is when it actually gets a little bit tricky, because we're moving into these two middle groups. And again, how do we tell which is more or less deshielded? Like I mentioned earlier, this group is going to be less deshielded, as this alcohol group is equatorial, or farther out of the plane, whereas these hydrogens here, or protons here, are closer to this alcohol group due to the fact that it's axial. So I'm going to go ahead and take these two, but there's actually something that I'm noticing here. With the number of peaks that we have, this is not going to line up. So that tells me that these hydrogen groups are actually going to be in their own environments. So, therefore, labeling these separately is the only way for it to work. And again, just looking at how this is drawn into which is closer to the alcohol groups here, we're actually going to see that this hydrogen or proton is going to fulfill this peak, whereas this hydrogen, the green one, not to gum it up with too many arrows, will actually fulfill this. This is actually a quite difficult structure, and that proves why. So now moving on to our fourth peak, definitely going to be this group here. Two hydrogens, that makes plenty of sense. And they're much less deshielded than these hydrogens that are attached to the alcohol groups. So those two are going to be referenced here. And finally, moving on to our last peak, this actually makes it quite simple for us, because we are going to see that these two hydrogens here that are directly attached to the alcohol groups are going to be the most deshielded, most downfield, because of their proximity to those. So that makes perfect sense that both of them together would be on this peak. So now that we have a structure that really lines up well with this proton NMR, and one can see as to why things are shifted with this chair structure due to the axial and equatorial nature of the alcohol groups, and even though it is slightly confusing with these two protons being in their own environments, we now have a solid structure that can represent this well. So due to that fact, we have completed proton NMR, and we are actually going to move on to carbon NMR. I'm going to go ahead and label that for us. So now, in carbon NMR, we are no longer going to be looking at the hydrogens or the protons. We are actually going to be looking at the carbon groups themselves. And again, the best structure to draw here is most definitely the chair structure, because it really shows us the deshielding in its nature. So I'm going to go ahead and do that really quickly here. Of course, one group axial and one group equatorial again. And now we really have to take into account the symmetry here, because as we can see in this graph of carbon NMR, we only have 3 carbon groups. But that actually makes very good sense because of the symmetry we're seeing here. 1, 2, 1, 2, 1, 2. They're directly in line with each other. So we can label these carbon groups together. Again, working from right to left, we're going to want the least deshielded carbon groups, which are again going to be these 2 carbon groups, as they are farthest away from the alcohols. So those two alike will fulfill this requirement. And again, this is going to put us on a path of fulfilling all of our carbon groups to only 3 peaks. Simply, we will just move in as we are working right to left. These 2 carbon groups here will be the second most deshielded, because they're in between these farthest away carbons and these closest carbons to the alcohols. So we will label that as such. And finally, moving inward to the direct carbons attached to the alcohol groups, those and their symmetry will align to fulfill this 3rd peak. And now we have a successful proton NMR as well as a successful carbon NMR, as the d-shieldings all work appropriately in both, and I believe this is a very solid structure for the graphs that we have been seen and given here today. So, now that that is complete, I thank you very much for your time and for listening. Again, this is Tyler Jones of the University of Illinois Springfield. I appreciate you for listening, and you have a great evening.